Hello everyone, thank you for joining me today. My name is Minim and today we're going to be looking at moments. So we have a few learning objectives and that's to be able to define what a moment actually is and to be able to understand the equilibrium condition for moments and to recall the moments equation, which is moments in Newton meters is equal to force in newtons multiplied by the perpendicular distance. Okay, so now we want to understand what actually is a moment. Well, a moment is nothing but a turning force. Okay, I realize that it's a fancy new physics word and why can't they just call it rotating? I get it, but we simply have to understand that every time there is a rotational force occurring or an object is rotating along a pivot, right? So that's something that we're going to look at as well. A pivot, or the fancy word for a pivot is a fulcrum, we get a moment's force. Okay, so I'm going to do things a bit differently and I'm going to introduce the equation straight away. So capital M for moment is equal to force multiplied by distance. But now this distance is a bit different. This distance is the perpendicular distance from where the force is applied. Okay, so let's label our diagram here. So this is a very classic example, a seesaw for describing moments. So right there in our middle where the I guess you could say the poles are actually balanced is called the pivot, right? Now if you read older textbooks or if you read around moments, you'll realize that this is also called a fulcrum, so I can write that as well. But usually at GCSE we stick with pivot. Okay, so the middle bit where the balance point is the pivot, and then on each side we have forces acting upon it. Now what are these forces? Well, in the seesaw case, it's the weight of the actual person sitting on the seesaw. Now we understand that weight is always acting downwards, so we can do it this way, right? So weight acts downwards. Now, because this is the seesaw is kind of unbalanced, this is going to look a bit weird, but say I redraw our seesaw on the side right now. So I have like that, and then I have my weight here, and I have my weight here. Now, the distance is this distance here, the perpendicular distance from the pivot to the force applied. So that is my D1, and that is my D2 for second distance. Okay, ideally we should have an equal spacing distance between the two weights applied, but you'll realize that in levers, which is where you can have a very large distance and some force applied there, and that can translate to a huge force on the other side over a very small distance. That's something that we'll look at later in levers, but here is the simple diagram for a moment setup. So we can see here that we have one force acting downwards, or rather one weight acting downwards, because remember weight is a force, right? Acting downwards this way on the left and the right sides, and then we have their distances from where the force is applied to the pivot being our distance. Okay, so now let's put down our units in our equations. So our moment is measured in a brand new unit called Newton meters. Now why is that? Well, force is in newtons and the distance is in meters, and we're just multiplying the two, so it's Newton meters, right? That just makes sense. Okay, now I want to introduce to you a brand new thing called the equilibrium condition. Now what is that? Well, the equilibrium condition, let's have a look at what equilibrium actually means. So equilibrium means when all things are equal. So when the seesaw is equal, well, what's happening? The seesaw is flat. Okay, so no sort of change is happening at all. So for the seesaw to be flat, or for it to be in equilibrium, the clockwise moments need to equal the anti-clockwise moments for a system to be in equilibrium. So what does that mean? So that means that the moment acting this way around, because remember we can split the seesaw into two halves, right? So on our left half, the seesaw is being pushed down. So if our left side is being pushed down, we're rotating anti-clockwise. Now if I push down my right side, my seesaw will rotate clockwise. So on my left side I have anti-clockwise moments, and on my right side I have clockwise moments. Now, if we think about this, right, if my anti-clockwise moment is, say, minus 10 Newton meters, and then I get my positive clockwise moment 10 Newton meters, I just get back to 0, right? I get flat. So that's why clockwise moments, when clockwise moments equal anti-clockwise moments, a system is in equilibrium. Okay, so now let's have a look at a worked example. As always, we're going to highlight all of our keywords. So two children, A and B, are sitting on a seesaw as shown in the figure below. All right, the seesaw is balanced. Okay, so we're looking at equilibrium. Now, use the following equation to calculate the moment of child B about the pivot for the seesaw. So we're looking at the force B here about this pivot over here. Okay, so now let's continue highlighting. Moment equals force times our distance. Give your answer in Newton meters. All right, so that's because it's written in the question line itself. That means that there's something in the question that we have to convert. So I'm just going to rewrite our equation, but in symbolic form. M equals FD, right? Moment equals force times by perpendicular distance. Now, we have our force. That's 280 newtons right there, right? 280 newtons acting downwards. And now we need the distance here, which is 90 centimeters. Okay, but we need to give our answer in Newton meters. So we need to convert 90 centimeters into a meter. And there are 100 centimeters in a meter. So we just do 90 divided by 100, and that gives us 0.9 meters. Now all we do is substitute our values in and multiply them together. So, moment equals force, 280, multiplied by distance, which is 0.9, and that gives us 252 Newton meters. Okay, that's our answer right there, 252. And that is 2 marks right there. Okay, so now let's have a look at a harder worked example. Now, as always, we're going to highlight all of our keywords. So, a drum is hit by a beater attached to a drumstick lever. The drumstick lever is attached to a foot pedal by a chain as shown in figure 1. Okay, so we have our figure 1 right here. It looks kind of complicated, but by the end of this question, you'll realize that these questions aren't as complicated as they seem. So, the drummer's toe pushes with a 1.5 Newton force on the foot pedal. So, that's right here. The perpendicular distance between the pivot to the force is 0.12 meters. The perpendicular distance from the pivot to the chain is 0.2 meters. Calculate the force on the chain acting on the foot pedal. Okay, so we're trying to work out this unknown force here, given one force and one moment. So in all of these moment questions, there's an underlying assumption, okay? So what we assume is that it's in equilibrium. So the system is in equilibrium. So system is in, this isn't part of the answer, this is just so you understand it, in equilibrium. Okay, now that the system is in equilibrium, what sort of assumption does that tell us? Well, that tells us that clockwise moments equal anti-clockwise moments. So we can see that the force of the chain on the foot pedal is acting upwards, and we can see that our force that done by the toe is acting downwards. So the force on the foot pedal is the clockwise force, or rather part of the clockwise moment, and the force of the toe on the foot pedal is part of the anti-clockwise moment. So let's work out the anti-clockwise moment. So I'm going to do that symbol to show you anti-clockwise moment. Now, moment is equal to force multiplied by perpendicular distance. Both of those values are given to us, and that is 1.5 multiplied by 0.12 meters, and that gives us a 0.18 Newton meters. Now, anti-clockwise moments equals clockwise moments. So if we switch this around to clockwise moments, again, we have moments is equal to force times our distance. We have our moment, that's 0.18. So let's rearrange the moments equation for force. So we do moment over distance is equal to force. Now we just substitute our values in. So we get 0.18 Newton meters, which is our moment that we just calculated above, the anti-clockwise moment. And our distance is from the pivot to the chain, and that's 0.2, because remember, it's always moments about something, usually about a pivot. 0.20 meters, and that equals 0.9 newtons. So that is our answer right there. So you can see that a complicated looking figure and a long sounding question doesn't really turn out to be that hard at all.